Welcome to Vostok Station, Antarctica. Winter here gets a lovely 0 hours of sunlight a day, and temperatures can drop to record lows of negative 89 degrees Celsius. Even so, 15 to 30 insanely dedicated people frequent the station almost every year, braving some of the harshest conditions Earth has to offer. And it's all to collect samples of ancient ice buried kilometers under the surface. These deep ice cores contain priceless clues about Earth's prehistoric climate, going back 420,000 years, long before Homo sapiens even evolved. But how can scientists even make sense of these clues? In this video, we won't just talk about what these ice cores are and how they're formed, but also how researchers read them, explaining the truly mind-blowing physics, chemistry, and biology behind these frozen time capsules. Let's get into it. Let's rewind the clock about 500,000 years to a dark frozen winter on the East Antarctic ice sheet. Here, the average snowfall is just over 2 centimeters a year, making it one of the driest deserts on Earth. Even so, a little bit of snow is still falling, piling up millimeter by millimeter as microscopic shards of ice. When summer comes, the temperature is still about negative 44 degrees Celsius, well below the freezing point of water, so the powder sticks around. By the next winter, when our snow is a year old, it's earned a new name, fern. Another year comes and goes and deposits another tiny new layer of snow on top of our fern. This process continues year after year, stacking a little more snow each year and weighing down our fern bit by bit. Once we get about 95 meters of snow on top of our first layer, a painstakingly slow 25 centuries later, something new is happening to our first layer of fern. The weight of the snow is so great that our fern crystals undergo a process known as sintering. Here, the individual crystals fuse together and form dense glacier ice, trapping any remaining air between the original snowflakes in high-pressure bubbles. The moment these bubbles are sealed by the sintering ice around them, they act as little time capsules of Earth's atmosphere, locked away in cryostasis. And there they remained for hundreds of thousands of years, getting crushed down deeper and deeper with every year, kilometers from the surface and completely unaware of the rest of the world. That is until 1998, when a drill made it over 3,600 meters below the surface and extracted our first layer of ice, along with every bubble of air trapped within it. Now that they had extracted these time capsules, scientists were riddled with questions about what the ancient atmosphere used to look like. But how could they possibly sample such tiny amounts of air? The first step was to take small samples of the ice cores, place them in a sealed, frozen, stainless steel vessel under a vacuum, pulverize them, and collect any gas that escaped. Since each bubble was a sample of the atmosphere, they contained the same gases that we see today, like oxygen, CO2, and methane, but at slightly different concentrations. Using gas chromatography and mass spectrometry, they were able to record these levels of CO2 and methane going back 420,000 years. So what did they find? It turns out CO2 naturally fluctuated between 180 and 280 parts per million for the whole ice core. Methane followed a similar pattern between 300 and 700 parts per billion. For context, today's CO2 level is roughly 425 parts per million, and our methane is 1,927 parts per billion, a roughly 50% increase in CO2 and a 175% increase in methane since pre-industrial times. Okay, so we know greenhouse gases were way lower in the past, but how can we infer the temperature from this? After all, greenhouse gases can only tell you so much about the past climate. Well, one thing researchers looked for were ratios of certain isotopes, as the ratio of heavy hydrogen to light hydrogen can be used as a paleoclimate temperature proxy. Wait, hold up. Isotopes? Paleoclimate? Proxy? What's going on here? Let's break it down. To really get a full understanding of what scientists are looking at in ice cores, we need to go over some chemistry first. I know this can be a little daunting, but stay with me. I promise this will give you a deeper and more rewarding understanding by the end. So as you may remember from chemistry, atoms are made of protons, neutrons, and electrons. For this, we only care about protons and neutrons. Protons are positively charged particles, and the charge, or the number of protons, defines what the element is. So, for example, if you have 8 protons, you have oxygen. 3 protons would give you lithium, and the simplest atom, hydrogen, can only have 1 proton. If you try to give it a second proton, you've got helium now. Neutrons, however, are neutral, meaning no charge, so you can slap some extra neutrons on our hydrogen without changing what the element is. Typically, hydrogen has one proton and no neutrons. We call this hydrogen 1, with 1 being the sum of the protons and neutrons. However, just about 1 in every 6,400 hydrogens on Earth has an extra neutron, bumping our numbers up to 1 proton and 1 neutron, and getting the name hydrogen 2, also known as deuterium. These two hydrogens are known as isotopes, elements with the same number of protons but different numbers of neutrons. And because deuterium has 1 more neutron, it's about twice as heavy. Okay, so we have our two hydrogen isotopes, light hydrogen 1, which I'm just going to call hydrogen from now on, and heavy deuterium. But what does this have to do with the climate? Let's zoom way out to our global water cycle. All water molecules consist of 1 oxygen atom and 2 hydrogens to make that classic H2O. The hydrogens on the end here are usually just our light hydrogen, but sometimes one of them is deuterium. A water molecule with our light hydrogen will therefore be light water, and a water molecule with our heavy hydrogen will be heavy water. Now, let's imagine how light and heavy water act in our water cycle. Because of their different weights, they don't exactly behave the same way. For example, when water is evaporating off the surface of the ocean, our light water will always evaporate quicker than our heavy water. This means that clouds just above the equator, where most of Earth's water evaporates from, will be enriched in light water, and the ocean will be enriched in heavy water. This process of isotopes separating based on weight is known as mass fractionation. As these clouds spread out and move towards the poles, they will rain and snow as the air gets colder and the water condenses. Now the heavier water will precipitate first, leaving even more of the light water vapor in the cloud. This process continues, the water vapor getting isotopically lighter and lighter as more heavy water rains out until it reaches the poles. Here, the last bits will snow out, now super enriched in light water and depleted in heavy water. Now here's where the climate comes in. The colder the air that our water vapor had to travel through to reach the poles, the more condensation and the more heavy water that rained out. This means that during cold climates, the snow reaching the poles has even more heavy water stripped out of it, giving a lower deuterium to hydrogen ratio. However, during warm climates, not as much water vapor will precipitate, there's less mass fractionation, and there will be a higher deuterium ratio in our snow and ice. So if your ice is low in deuterium, it was a cold climate. And if your ice is higher in deuterium, then it was a warmer climate. And just like that, we've discovered a proxy, or a way of preserving what Earth's temperature used to be like. And using proxies to reconstruct what ancient climate used to be like, well, that's paleoclimate. Congratulations, you now know how to read an ice core. Go ahead and update that resume. And if you've made it this far in the video, consider giving it a thumbs up or a subscribe if you haven't already. It really does a lot to support the channel and climate science on YouTube. So now that we've got that all cleared up, what does our ice core tell us about the prehistoric climate? This graph represents levels of deuterium found in our ice samples. As you can see, it fluctuates up and down over the last few 100,000 years. Remember, deuterium ratios go up when it's warm and go down when it's cold. And so whenever we see a rise in deuterium, it correlates perfectly with the spikes in our greenhouse gases CO2 and methane. And since the deuterium record and temperature are correlated, we can then calculate how warm or cold the Earth's temperature used to be. As you can see, there are brief warm periods a degree or two warmer than pre-industrial temperatures that are followed by long cold ice ages up to 8 degrees colder. These 5 warm interglacial periods seen here line up perfectly with geologic evidence. And while yes, there have been brief periods in the past where temperatures have been slightly higher than modern averages, CO2 and methane levels are far higher today than at any point in the record. If warmer temperatures have been reached with less greenhouse gases in our past, this implies that we have not yet seen the full warming potential that our carbon emissions could cause. Just another reason why we need to stop burning all fossil fuels as soon as possible to allow our climate to stabilize. While a full understanding of the entire climate is far more complex than we can tell just by measuring gas bubbles and glacier ice, it is absolutely mind-blowing that we have been able to reconstruct so much about Earth's past given such tiny time capsules. And ice cores are only part of the picture. Scientists have also looked at tree rings, coral skeletons, underwater sediments, and even ancient stalactites to connect the isotopic dots and reconstruct the paleoclimate from all over the world. And today, thanks to the excruciating dedication of a handful of scientists at the South Pole, we're able to peer back in time 420,000 years to better understand the ways in which our complex miracle of a planet functions. Thanks for sticking around to the end. As always, all the sources are linked down below. If you enjoyed this, make sure to like, comment, and subscribe to support Planet Zero. I'll see you next time.